Carbon, an element so important it has its own cycle. Welcome to my presentation on carbon, and I'm glad you're here. Before I begin, I want to thank Stephen for the idea, this website, this app on the iPad or from my iPad, and it's amazing. It was well worth the $2.99 it cost to put it on the iPad. And if anybody else has any questions about flipping lectures for classrooms, you can go ahead and send me an email, and I'll send you something back. It's one of my areas of study right now, and now I have another tool in my repertoire. So thanks again, Stephen. So with 6 protons and on average 6 neutrons, carbon is one of the most important elements that is known. It's one of the most important elements to life. It's the single most important element from the Industrial Revolution, which allowed us to be learning about carbon right now and the way we're learning about it. Carbon is known as the fundamental building block of life. It possesses the ability to bond with almost every other element, and it can bond with itself in a variety of ways as well. It's the fourth most abundant element by mass in the entire universe, the 10th most abundant in Earth's crust, and the second most abundant in humans, right behind hydrogen. In its purest form, carbon is a conductor, but is pretty resistive. But it is a component of many, many different insulators. It has the highest melting point and sublimation point of any other element. Carbon is the sole component of a diamond, as well as graphite. And the isotope carbon-14, the unstable radioactive isotope, can be used to diagnose and treat a variety of diseases, the most known which is cancer. We can use molecules containing carbon to create and destroy nearly anything we can imagine. And carbon, it's an absolute party animal. It's a shamelessly promiscuous element that will latch itself to nearly any element known in a variety of different ways. So how does it do this? Carbon is what's known as tetravalent, tetra meaning 4, and so it's capable of creating 4 covalent bonds with other atoms. Now, its atomic number is 6, which means it has 6 protons as a nucleus, and under normal circumstances, its outer electron shell has 4 electrons and then 4 empty spaces to make up its octet. This makes it an ideal candidate for bonds of different strengths with a variety of other elements. Okay, so these bonds that carbon creates with itself and other atoms makes it the backbone of sugars, fatty acids, amino acids, DNA, and these are the most fundamental compounds in all of biology. There isn't any other element that can form bonds in the same way that carbon can. Carbon's capability for creating bonds also makes it a major component in most of our fuels. So heptane, which we see here on the left, and octane we see here on the right, they're the main components of gasoline, and they're based on rings of 7 and 8 carbon atoms, respectively. Heptane was 7, octane was with 8. Alcohols, like ethanol, they're built out of at least 1 carbon atom combined with hydrogen atoms and a hydroxyl group, which is just a single oxygen and hydrogen. Methane, our natural gas, it's a molecule that has a single carbon atom and 4 hydrogen atoms. So all these fuels, they work by breaking down the strong covalent bonds that hold carbon atoms together and then releases the energy that they store. And we see here in the picture below that there's a 4-stroke cycle engine. Fuel goes in, valves close, compression happens, there's a spark, and then out comes carbon in a different form after releasing most of its energy, and it creates carbon dioxide, another form of carbon. Now, this tetravalent property that carbon has means that it can combine itself with itself in different ways. So I call this being self-adhesive. It can make very, very strong single, double, triple covalent bonds with itself with other carbon atoms. So the resulting and the variable geometry means that the diamond can form from the exact same materials as graphite, but through a different process, which is amazing. If we look at the top picture here, we have graphite, and in graphite we see just to its right, its atomic structure, its molecular structure shows us that there are these strong covalent bonds between carbon atoms, and it forms these sheets. And then there are weaker bonds that attach the sheets together. Now, what this does is it makes graphite an outstanding lubricant. So, as graphite is rubbed, the bonds between the sheets break, making it very slick and slippery. So, it's used as a lubricant. It's also what's in the quote unquote lead of our pencils. And we leave little sheets of graphite behind whenever we write. Pretty interesting. Now, the same carbon atoms can form a diamond, and diamond has all very strong covalent bonds, making it have a hardness of 10, whereas graphite has a hardness of between 1 and 2. Diamonds, many of them now are made synthetically when we use them for things like industry as cutting tools. But these very strong bonds give them a hardness of 10, and they're very difficult to break. Now, if we combine carbon atoms in other ways, it can form what are called carbon nanotubes. And these are the strongest molecular structures that modern science has created and found. These what are called fullerenes. These are shells of carbon whose properties include super conductivity, high strength. We can use these things in a variety of ways. And right now, people looking into different types of medicines are talking about delivering medicines via these nanotubes or buckyballs, fullerenes. There's all kinds of different applications, computer applications. Everything's coming out, and it's based on carbon nanotube technology. A pretty amazing thing. It's going to drive the future. Now, here at home, carbon permeates our landscape, and it's a reminder of tropical days in the past. Our limestone bedrock speaks of warm, shallow seas in which calcium carbonate can precipitate, and our peat and coal deposits tell of a wet and luscious swampy environment following land being brought up and the tropical warm, shallow seas being taken away. So if we look in the right here, we have a picture at the top of chunks of coal that were created from years and years and years of vegetation falling in swampy environments and never quite fully breaking down. We burn this, combust it, take the energy, and carbon dioxide is made. Below this, we see another form of carbon. This is calcium, the structure of calcium carbonate. And calcium carbonate is what the Michigan bedrock is made of. Here below that, we see a picture of my son and I in a cave in Indiana with the stalactite and stalagmite structures and the columns right behind us. And this is formed from calcium carbonate that came with water as it dripped. Michigan doesn't have caves like this. This is in Indiana, actually, south of the greatest extent of the last glacial advance. But in Michigan, we do have a lot of what's called karst topography, which is when our limestone bedrock is eroded away by the acidity in water, in rainwater. Now, the isotope carbon-14 is radioactive, and it occurs naturally. It occurs in nature. This decays into nitrogen-14 with a half-life of 5,000 years, and carbon's abundance means that it can be used to fairly accurately date many different biological artifacts, such as bone, cloth, wood, plant fibers, up to about 50,000 years old. And so we see here on the left, we see a diagram of this part of the nitrogen cycle, the carbon-14 cycle, and how it gets into living things, and we can eventually take that and accurately make these datings. We see in the past, there's the radioactive decay curve of carbon-14, okay? Only going up to about 29,000 years, though, on this. So this makes it instrumental in archaeology, for example, for cataloging historic and late prehistoric human history. It's radioactive and its beta decay also make it useful in medicine for locating malignant tumors. It's used in research. In pharmaceutical research, it's used as a tracer to ensure that drugs that might come in the market are metabolized without forming harmful byproducts. It's also used in other research in agriculture, pollution control, and archaeology. So carbon is fundamental in every biological process, every plastic, and everything that was ever part of a living thing. It's nearly impossible to imagine a world without carbon. We certainly wouldn't exist, and neither would most of the living things that most of the things we use in our everyday lives. It's truly the fundamental building block for life. Carbon's history is pretty important, or well, pretty interesting. Excuse me. It's been known since ancient times, and in forms of soot and charcoal, graphite, and diamonds. The Egyptians and Sumerians used it for reducing copper and tin ores in the manufacture of bronze. Okay, so bronze tools and weapons. Ancient cultures did not realize, of course, that these substances they were using were actually different forms of the same element, carbon. The eminent scientist, the French scientist Antoine Lavoisier, he actually named carbon and also figured out that carbon and graphite and some other elements were made of, or other items were made of carbon. So he named it, and he carried out this variety of experiments to reveal its true nature. In 1772, he and some other scientists, some other chemists, pooled resources together to buy a diamond. Now they placed this in this closed glass bell jar. And if you look at the image right here, we see this humongous magnifying glass is what it is. And Antoine Lavoisier and other chemists were doing combustion experiments. And so he put this diamond in here. And they focused the sun's rays on the diamond with this humongous giant magnifying glass. And eventually the diamond burned up. So he noted the overall weight of the jar was unchanged, and that when it burned, the diamond had actually combined with oxygen to form carbon dioxide. So this is when he concluded that diamonds and charcoal are made of the same element, carbon, which he named. Carbon seems to have been forgotten by many as the most essential element in mankind's progress and our being. So it's now the stepchild element, and it's the founding member of the greenhouse gas party. And what we see right here is greenhouse effect, the natural versus the human enhanced greenhouse effects, where carbon is blamed for most of our greenhouse effect, the increased amount of carbon dioxide released by humans through combustion of industry, of vehicles, etc. So there's a balance that we have to strike at some point, a balance we have to strike between the carbon we use for everyday life, right, and the carbon that's essential for us to live. Very interesting. I suggest you learn more about this carbon, the life's most important element, and you can explore with the following resources that I used, as you see below, for the presentation, and there are many, many more on the web. Thank you very much.